lab as well as taking the test?
I don't plan on it
Okay.
unless you just really want to.
I'm good.
I figured not, but yeah, we will just do the exam. My intent is to, try to keep it to 50 minutes, even though it's during lab time. Right? I don't want to give you an exam that takes 3 hours. And sort of, I may have mentioned this to one of you in office hours. Because this is sort of such a small amount of material, even though all the exams in this course add up to 400 points, they may not be all 100 points each, right? And so this exam may be a little bit lighter, right? Maybe around 80 points or something like that. I'll have to sort of finalize my draft and see where it ends up. But some exams cover a bit more material, and so they may be a few more than 100 points, and this one a little bit less than 100 points. But overall, 400 points for the 4 exams. All right. So let's get this show on the road. We are in chapter 6 now. And so that is UV vis spectroscopy. And I'm going to start with hopefully what is review from Gen Chem, talking about wave mechanics and things like that. When we talk about light, of course, we have to go back and do some of this review. I know that I did a bit of this when we were in chapter 2, talking about quantum mechanics, but I just want to make sure that we are all comfortable with these kinds of equations. Oops, that thing. Right. The energy of a photon is h times nu, the frequency, and we can rearrange that to get hc over lambda because of this relationship between the speed of light and the frequency and the wavelength of that light. Again, since you're making your note cards for the exam tomorrow, yes, you're making your 3x5 equation card. H is 6.626 times 10 to the negative 34 joules seconds. And C is 2.998 times 10 to the 8 meters per second. I am A-okay if you use 3 times 10 to the 8. I know that it's quicker and faster, but in a situation where you might need a few more sig figs, 2.998 gives you a few more sig figs. And so we will sort of come back and think about these as we talk about power and sort of how many photons are hitting a detector, things like that. So we'll think about that when we get there. Okay. All right, really that's all. I know we covered this in chapter 2, so I just wanted to remind you of those equations since you will see them on the exam tomorrow, more than likely than not, so that you had them on your card. So really getting into spectroscopy and the Beer-Lambert law. Beer's law, Beer-Lambert law, we talked about this in our lab last week, our limit of linearity stuff. And so to really think about this, we need to go back a step and talk about transmittance. Because transmittance is actually what's being measured, right? Instruments don't measure what's being absorbed by the solution. How could they possibly measure that? What they measure is how much light gets through the solution. And so transmittance, right, is the amount of light transmitted through the solution And when we talk about amount of light, we will often speak about it in terms of power, right? Power is, of course, some energy over time, right? So joules per second is something that we'll use commonly. That's watts. And so when we talk about transmittance, T, it's about the power of a beam divided by the initial power of that beam, right? And so when we think about this, this is the power through the sample. Whereas P naught is the power through the blank. Right, that initial power that we set as our background, that we set as our zero. And they worked with transmittance for a while. If you have done a lot of IR spectroscopy, you know that the y-axis on an IR spectrum is still percent transmittance, right? And so, you know, this is still a useful bit of useful to know. But when we talk about UV vis specifically, we don't tend to talk about transmittance. We certainly could, but we talk about it in terms of absorbance. And so the absorbance is related to transmittance, and it's the negative log of T. And of course, if we know our log rules, we know that T is 10 to the negative A. Those are useful going back and forth. If we want to sort of figure out our limit of linearity or something, and we know that we can go up to a certain concentration on a particular instrument. If we change instruments and we know that our power is going to go up by 50%, we can sort of figure out, we can back calculate how wide that linear range could be given that new power by figuring out what the new absorbance would be and going from the new absorbance maximum to the new concentration maximum. So we can do a lot with going back and forth between power, transmittance, absorbance, all these interrelate. And so tying this into what we talked about in the lab last week, that Beer-Lambert law, we know that the absorbance is equal to, I'm going to take it as simple as possible first, and then we'll see the one that maybe we're more familiar with. A is equal to ABC. This is a very generic form of the equation. Of course, we know absorbance is big A, little a is the absorptivity. B is the path length, often given in centimeters, but not always. And C is concentration. We're very used to seeing this in molarity, but it could be any kind of concentration. It could be molality, it could be parts per million, it could be grams per liter. It doesn't really matter what our concentration unit is. If we just use sort of the blanket absorptivity term, then it's not necessarily molar absorptivity, right? And so that concentration and the absorptivity units need to match. But other than that, we can use pretty much any concentration unit. Another term that you'll see sort of replacing absorptivity is extinction coefficient. And the extinction coefficient, like that's just how quickly is the light extinguished as it goes through a particular sample. That's where that term comes from. It sort of rolls in the fact that not all of the light that's lost is absorbed, some of it is scattered, and so it takes into account those other processes that are other than absorption that are occurring in the sample. The one that we are used to seeing, of course, is A equals epsilon Bm, where epsilon is our molar absorptivity, or I'm going to say our molar extinction coefficient. B is again our path length, and then because we're talking about molar extinction coefficient, and this has to be the molarity. And most of you figured it out last week what the units on an extinction coefficient should be, right? It's 1 over whatever our concentration units are times our path length units. And that's because absorbance is a unitless number, right? We have power over power to get transmittance. Of course, those units then cancel, so transmittance is also unitless. And when we take, when we use logs, of course, we can't have units inside a log. And so absorbance is also unitless. So 1 over molar centimeters or liters per mole centimeter, right? These are both reasonable terms. If we were talking about ppm, then it would be 1 over ppm centimeters, or grams per liter, liters per gram centimeter. Your absorptivity coefficient, your extinction coefficient can have all kinds of crazy units depending on what you use in terms of your concentration. Okay. Any questions about the Beer-Lambert law? Yeah. We know it should be linear, right? We know that this corresponds to y equals m, these two are m, times x. We don't have a plus b, right? Because when our concentration is 0, our absorbance better be 0. If it's not, something's messed up. And so we don't have a plus b because hopefully that is 0. Sometimes in like an Excel graph or something, if you have a small residual leftover y-intercept, you can force that trend line to 0 and sometimes get better values, more accurate values for the extinction coefficient. All right, so we talked in lab again about how at some point this linear equation, this linear trend, loses its linearity. And so let's talk a little bit about why that could be. So these deviations from the Beer-Lambert law really are deviations from linearity. And so thinking about this, the first of these is going to be due to concentration. Right? And we saw this a bit last time. It's sometimes referred to as internal screening, but they're really separate factors, but it's hard to really determine which of these takes over first, right? So you can imagine that as we increase concentration, right, if there's not enough photons for every molecule to get his own, then we're going to eventually reach the limit where there's no more photons. And that absorbance is going to max out, even though not every molecule has received his photon, right? And so if we have too many molecules slash not enough photons, right, we're going to get that curve that we saw in lab where we're linear for a long range in concentrations, but then at some concentration it starts to level out. And so we just don't have enough photons for every molecule to have its own. And so we're adding these molecules to our concentration without increasing our absorbance because we don't have enough photons to go around. Internal screening is the phenomenon whereby the solution is so concentrated that if molecule in front, a molecule closer to the light source, right here, if he absorbs a photon, or even if he doesn't absorb a photon, right, he's going to cast some kind of shadow. We don't think about individual molecules casting a shadow very often, but if our solution isn't moving very much, then if we have a molecule that sort of photon-wide line behind him or molecule-wide line behind him is not going to have any photons populated in it, right? Remember, our light is traveling in a collimated beam, and so there's no movement up and down in our sample, right? Our light is traveling in straight lines. It's not traveling like this anymore. And so if one molecule in front absorbs, then that molecule behind is left without a photon to absorb. And so again, this is something that increases as concentration increases, where that even if there are photons available, the molecules that are sort of in the second and third line from the light source are unable to really absorb due to this screening. And so these really go hand in hand. They're both due to concentration issues. One being we don't actually have enough photons in our light source. The other being it's concentrated to the point where the molecules are sort of shielding one another from the light source. Okay. A second issue could be some stray light. Right. This is an issue that would sort of affect the whole curve rather than just this nonlinear portion. But if we had stray light that was able to make it into the detector, then, so let's say, for example, we put our blank in, we zero our instrument, we open the instrument, take our blank out, and put our sample in. If we forget to close that instrument top or something, then there's extra room light that's getting into our sample that didn't get into the background, the zero. Right? Yes, this is a human error rather than an instrument error usually, and so correctable, but still it's something that we should be able to notice, right? And if we have more light, how is that going to affect our curve? This was one of your questions on the lab. If you have, I mentioned it's more powerful, but go ahead, Baja.
Okay, so like more intensity, doesn't that reduce the effect of the deviation of stray light on the transmitted? Or
Absolutely, absolutely. If we have a more powerful lamp, then so let's say our lamp is 50 watts or something. The amount of stray light that gets in is going to be much less than that, and so it's going to cause much less deviation than if we had a 7-watt lamp. So just for sake of argument, imagine that the room light is 1 watt, right? That's stray light. If you let 1 watt into a 50-watt bulb, that's an extra 2%. If you let 1 watt into a 7-watt bulb, that's an extra 12.5%, right? And so the more powerful bulb you use, the less stray light really matters, right? But generally speaking, the more light we have going through a sample, how does that affect our curve, our linear curve? Does it sort of think about it as increasing the slope or decreasing the slope?
Wouldn't it cause the flatter portion to be more straight because there was more light getting through?
That's right. So let me use a different color here for our stray light. If we had extra light going through the sample, it would tend to flatten out this curve a bit. So we had more linear range before we started flattening off. Okay. The issue with stray light, usually more linear range, that's a good thing. Let all the stray light in, right? The issue with stray light is that it's not monochromatic, right? And so we're not getting whatever single color we're interested in getting, where we're doing ourselves a disservice. Another issue could be that there's actually some reaction that's going on, right? If we have reaction in the cuvette, then that absorbance will change over time. And so you may have a really wonky calibration curve when you go to plot it because of whatever reaction is occurring in your cuvette. The last one to talk about is as we increase concentration, we could change the refractive index. We talked at the beginning of chapter 3 about refractive indices. We did a little practice problem with, how much light is bounced back when we go from air to quartz to water to quartz to air, right? And if our refractive index changes substantially from a low concentration solution to a high concentration solution, then we need to take new blanks with a similar refractive index solution, a similar refractive index blank, so that we can more accurately determine what that transmittance really is. And so, if we have something that really is going to change the refractive index of water by a whole lot, this is usually not necessarily ionic compounds, but if we think about dissolving organics in there, or if we have something that is not very colored, and so you can dissolve a whole lot of it in there. Hopefully all of you at this point have at least poured concentrated sulfuric acid. It's really kind of thick and viscous relative to water, right? Because it's 98% H2SO4. It doesn't take a whole lot of water to get it to dissolve. And so it's a very viscous liquid and has a very different refractive index than water due to that, right? So as we increase concentrations, that refractive index can change and change the amount of light that's being bounced back that we're losing due to those surface reflections. All right. Oh, yeah. So when we're taking our measurement, where do we measure, right? We always talk about lambda max is the best point to measure, but why do we measure lambda max? This chart is an image from our textbook. It shows sort of the real reason why we do it. If we look at the lambda max here, our absorbance is constant across the range. Whereas if we look at that same bandwidth in a different region, our absorbance changes by a whole heck of a lot, right? And so we choose lambda max because the absorbance is relatively constant across the bandwidth. What's the bandwidth of the instrument shown here?
6 nanometers.
6 nanometers, yeah, right. That's the width of these windows that it's showing us. Right? And so our instrument is not measuring a single wavelength, right? 520.0. Our instrument's measuring a bandwidth of wavelengths, maybe from 519 to 525. And all of that light goes to the detector. We want to have a pretty consistent absorbance across that, so that we are measuring as accurately as possible. What changes with absorbance? Remember, A equals epsilon Bm. If we choose a different wavelength, which one of these changes?
Epsilon.
Epsilon, absolutely. And so epsilon is wavelength dependent. And as you can see from this image, and if you've ever taken EVVis, you know that it can be very wavelength dependent, right? There are some wavelengths where epsilon is 0, right? The molecule just doesn't absorb at that wavelength. And there are other wavelengths where epsilon is 20,000. It absorbs a whole heck of a lot. And so because epsilon is so wavelength dependent, we want to choose that bandwidth. We want to put that bandwidth over a range where absorbance is constant, but really what we're interested in is epsilon being constant. Right? You can imagine that if we had a spectrum that looked similar to this, but let's say it had 2 peaks. Maybe we wanted to do something like this. We have another relatively flat region here, right? And we really have a third relatively flat region here in this valley, right? Because we have these 3 regions where absorbance, therefore epsilon, stays relatively constant, how do we choose which one? Why would we choose this over the other 2?
Is it because it has the highest absorbance?
Absolutely. The highest absorbance means that we're going to see the most change with concentration, right? It means the shortest linear range. So let's draw a little Beer's law plot of what we might expect here, right? At this point, we might expect to see something like this. For a small change in concentration, we're going to see a relatively big change in absorbance. But if we were to measure somewhere here, we'd see a much more gradual change because our epsilon is smaller. Therefore, remember that's the slope of our Beer-Lambert curve. Epsilon is smaller, so we actually get a longer linear range when we measure at a smaller peak. And it all depends on what kind of experiment we're interested in, right? If we're interested in measuring a very wide range of concentrations, maybe we should choose not the highest peak. But more often than not, we want to know a concentration very accurately. In order to know a concentration more accurately, we need a bigger delta between those concentrations, and that's easier to get when our epsilon is larger. But certainly there are instances where both are useful, but more often we use the absolute maximum rather than the local maximum. Any questions about that stuff? All right. Moving on to the good stuff. This is the part I like the most. So I'm going to draw what's called a box diagram. this is a diagram of boxes. Excellently named, I know. And these are sort of very simple schematics that I expect you to be able to reproduce. Right? I don't know if any of you are sort of electronics or hardware geeks, but if you look at a schematic for something, like a true schematic can be 5 or 6 pages long for a single part, and very detailed, give you all the dimensions, give you all of the wiring and how all the screw sizes fit together and all this stuff. So schematics can get super detailed, right? A box diagram takes each component of an instrument and just puts it in a box, right? We don't need to know anything else about that component other than its name. So it's a very simple schematic. And like I said, these are going to show up on exams. So the basic instrument design for UV Vis, right? We have our light source. And in that light source, we want to make it monochromatic. And so it goes to a monochromator. Once we have the wavelength of light that we're interested in, it goes into our cuvette, our sample. Then it goes to the detector. I want to make sure that I match what our textbook has. I think it goes to the, so then it gets processed by a computer or something. And so our textbook calls this a signal processor. And then the instrument tells us what the value is. And so there's some kind of readout. Right? Whether that's a computer screen, whether that's a little LED display that gives us absorbance, whatever. Okay. I've told you already, I'm interested in the nuts and bolts of things more so than the electronic side of things. And so we won't talk a whole lot about these two. We'll stick with the earlier part of the instrument. And so this is the simple box diagram for UV Vis. Right? We have some light source. We're going to get a single wavelength of light, or we know it's not really a single wavelength, but a bandwidth of wavelengths of light. We're going to pass that through our sample, and then we're going to detect that light somehow. And so we'll go through and we'll talk about these 3 components and how they're useful, what they're, what common types of each are. And then we'll sort of come back together and talk about sort of real life instrument design rather than just a box diagram. All right, so different sources for UV Vis. The most common, probably even still today, although it's rapidly changing, the most common is just a regular tungsten light bulb. This is just like a light bulb that you might have in your house if you haven't switched to compact fluorescents or LEDs yet. So if you have, gosh, I'm going to call tungsten bulbs old-fashioned, but if you have an old-fashioned light bulb, right, it's going to have this tungsten filament inside it. This tungsten has a pretty wide range in terms of the wavelengths that it outputs. Therefore, the wavelengths that you can accurately measure using a tungsten bulb, it outputs about 300 to 900 nanometers. And so you have a little bit of that UV. We usually think about UV starting about 400, between 350 and 400. And And so there's a touch of UV there, and it goes past what we think of as sort of the cutoff for visible light, which is about 750. So 400 to 750, 400 to 800, that's sort of the range of visible light. So tungsten covers that plus a little on each side. They're cheap to make, and they're relatively stable, right? So these are inexpensive. But they do require, do you want me to do cons in a different color? I've already done red. So a downside of a tungsten bulb is that they require a warm-up time. Right? They get stable after a while, but they require 20 minutes to 30 minutes of a warm-up time to reach that stability. The actual design of a tungsten bulb, if you've ever broken apart a household light bulb, you may notice that the coil in a regular light bulb is pretty spaced out, right? It's kind of drawn out. In a tungsten bulb for an instrument, those coils are right next to each other, right? They're about as close together as you can get them. And the reason is remember, the whole goal here is to collect all these light rays and put them in one direction for the sample. And so the closer together those coils are, the smaller the region where we need to collect the light from. And so we have the same sort of surface area of tungsten, it's just in a more compact region. So we get, so it's easier for us to collimate that light, for us to collect that light and send it through to the monochromator. On many sort of research grades, UV Vis instruments, a tungsten bulb wouldn't really cut it in the UV range, right? Benzene absorbs something like 220 nanometers. Lots of your conjugated, your not so conjugated systems absorb down around 250. And so you need something more than just tungsten if you're really going to look at a lot of these samples. And so oftentimes instruments would pair a tungsten bulb with a deuterium bulb. What's deuterium?
Hydrogen isotope.
That's right, hydrogen isotope. We write this as D2. So deuterium is hydrogen 2. But remember, hydrogen's always diatomic, and so it's really two deuterium atoms together. And so we abbreviate deuterium as D, since there's no element with a symbol D. We're safe doing that, and it's diatomic, so it's D2. This deuterium bulb, that's the spectrum that you have on your slide. And so you'll notice that molecular continuum for deuterium starts at about 400 nanometers and goes down pretty low to 165. I think usually most instrumentation cuts it off at about 190. The power gets really low, below 165. You can tell it's already on its downward trend here, even at 200. And so most instrumentation sort of cuts off the useful span at somewhere between 190 and 210, depending on the instrument. Right? But this goes down further into the UV. Right? It's a broad output, right? Broad spectrum for a UV lamp, and so I'll put about 200 to 400 nanometers. Right. A downside of deuterium lamps is that they are expensive, right? Not only is deuterium, not the most common thing out there. Deuterium in and of itself isn't crazy expensive, but one of the biggest issues is that a deuterium lamp and UV in general doesn't go through glass very well, right? If you've ever had to take a UV vis spectrum of something that's sort of deep in the UV, what kind of cuvettes do you use? Has anybody had to do this?
Are these the quartz ones?
Yeah, absolutely. We use quartz cuvettes if we need to look at something in the UV, because glass absorbs, plastic certainly absorbs in the UV. And so we have to use something that doesn't absorb UV light, and quartz is the material of choice usually. And so if we have a light bulb that needs to get UV light out of it, we've got to make at least some part of that enclosure out of quartz. And so we could make the whole thing out of quartz, which would be crazy expensive. But what generally happens is that if this is our light bulb base, here's our glass envelope, they call it. It looks kind of like a minion. And it has this little quartz window built into it. Right, they just, they form that glass bulb, and they take a little centimeter round quartz window, and they just fuse it onto that hot glass so that it makes that seal, but so that the UV can go through the quartz. Right? And so this is an expensive, there used to be a P there, and delicate. All right. The last two types of sources are much more common these days than they were even 10 years ago. And it's a push towards, less expensive materials, while these less expensive materials are becoming better and better at the same time. And so it's a bit of a few factors that are leading this. The first is LEDs. LED stands for light emitting diode. And up until a few years ago, it was not easy to get an LED that gave you a nice broad spectrum. Right? When I was a kid, for sure, there were no white LEDs. Right? There were red ones and green ones and yellow ones that would flash on a toy or whatever. But LEDs were not as common in scientific use. As they developed better materials, they managed to make some that have relatively broad white spectra. I mean, these days you can buy an LED flashlight for pennies, it seems, and it gives you a pretty nice white light, right? That wasn't the case 10 or 15 years ago. And so, as these technologies improve, we're going to use them to our advantage. And so these days, LEDs can be broad spectrum. They're even less expensive than tungsten. And really the only drawback for LEDs is in terms of power stability. So if we want a high power LED, that matches, you know, sort of a quality tungsten bulb, the stability of the LED is not quite as good as the stability of a tungsten bulb, right? We can go for lower power that has comparable stability, but as we go to higher and higher powers, the LED bulbs, the LEDs are just not as stable in terms of their power output. And remember that power output can contribute to additional noise, right? If we have power fluctuations in our instrument, then we're going to introduce another source of noise. Our background and our sample might not match in terms of initial power if we have this fluctuating power over time from our source. All right, the last source, and then we'll call it a day. The last source is a xenon flash lamp. Right. So if any of you have a camera other than your phone, it probably has a flash built into it, right? Those flashes are little glass envelopes full of xenon, usually xenon. If you have a fancy car, you might have xenon headlights in it too. When xenon's excited, it produces a pretty broad white spectrum, and so you get a lot of power. In a flash bulb, you get a lot of power in a short amount of time. Right? And so these are useful for a couple of reasons. The first is, since they're not on continuously, right? They only flash when you're actually taking a spectrum. They have a bit of a longer lifetime because they're not sort of constantly running. And so the instrument that we got in 2017, I think it was, the newer UV Vis we have has a xenon flash lamp in it, and it says it's good for something like 10 million flashes or something. And so, you know, even if it flashes 10 times a second, that's 1 million seconds of runtime, because it doesn't flash when it's not taking a spectrum. So there's a pretty long lifetime for the bulb. It doesn't require warm up like a tungsten bulb does. LEDs also require a bit of a warm up. The little handheld UV Vises that we used in lab last week, those have LEDs in them, and you know that it still asks you to wait for the 90-second warm up before you take a spectrum. So the xenon flash lamp doesn't need any warm up, and it covers a broad range. It covers about 220 to 900 nanometers, maybe even a touch, maybe even up to 1,000 nanometers. And so there's this really broad range, sort of encompassing both xenon and the tungsten bulbs. But because of that, we need a quartz envelope, right, for the flash lamp. And that makes it expensive. It's also the newest of these technologies for UV Vis, and that also makes it expensive. Okay? All right. We'll finish our talk in chapter 6 on Wednesday, exam tomorrow. This material is not on the exam, right? It's just chapters 2, 3, and 4. I know several of you have scheduled some question times, so I will see you shortly.
Dr. Davis.
Yes, sir.
Can I ask you just 2 really quick questions?
Really quick, let's do it.
On the homework, I noticed that there were some questions that like we hadn't covered yet, using some formulas that we hadn't covered yet. Do we need to put those formulas on our formula sheet?
You don't. We will. So those are the vibration kind of formulas from chapter 2. We will talk about that when we talk about IR and we talk about vibrations later in the semester. those are kind of play and chug because the equations are given in the chapter. And so I just wanted to, give you some practice solving those kind of problems. You do not need those equations on your equation card unless you haven't done your homework, in which case you would need those equations to do your homework on the exam.
Okay. And then on the equation card, you said no writing, like no words?
Right.
Okay.
Yeah. And so, I mean, what I don't want is I don't want you to say vibrations and then give the equation, or Beer's law and then give the equation. Like, I expect you to know that.
Okay. Are we allowed to write like what terms within the equation mean? Or do you just want us to memorize it?
Yeah, I think you should know it. Yeah.
Okay.
Yeah.
All right. Sounds good.
All right.